Tako, fino začeti. Danes pri nas pozdravljam dr. Senjanovića, ki je sicer še bo malo prišel na odri povedati nekaj o neutrinih LHC-u pa levo-desni simetriji, če jaz pravi. Tole je pa njegov postdoc sodelavec dr. Nemevša, ki bo pa zdaj dr. Senjanovića večkrat predstavil, zato da boste videli, s ki sploh prihaja, o čem je približen govoril. Pa ne preveč povedati, da bo še kaj za doktorja ostalo. Lepo prosim.
So, Professor Goran Senjanović was born in Beograd, in Serbia, but he grew up in Split, actually, on the coast. And after finishing high school in Zagreb, he then moved back to Beograd to finish his university studies there. After that, he moved to United States, to New York, to do his PhD. And that's where he started to work on left-right symmetry together with Professor Mahabatra. And he later stayed in the US for like 15 years, around 15 years, working at places, for example, at the National Laboratory, this is Stefan here. And he worked with famous people like Frank Winchester, the Nobel Prize winner. And then he was asked by another Nobel Prize winner, Abdul Salam, to come back to Trieste and form a phenomenology group. And he stayed there for last, say, what, 20 years or so? 20 years. And that's where we are working together now. And it's exciting for him to speak about this topic since he's been working, he's one of the fathers of seesaw mechanism, the mechanism of understanding the neutrino mass, and also one of the people who realized that our universe, our world can be left-right symmetric. And that's the topic. I don't want to say too much, right? So I'll leave it to Goran.
Okay. Thank you. Thank you. It's a pleasure. It's always a little scary when you give public lectures because you tend to fail. No matter how pedagogical you try to be, you fail, right? And yeah, it's hard to comprehend what we are doing. I'll try. It's been now maybe 2 or 3 decades, and especially in recent 10 years or so, that we know for sure that we have, and this has been a remarkable progress, the complete theory of all the particle interactions that matter. When I say all the particle interactions, I mean all of them except for gravity, and of course you may ask, how in the world can I ignore gravity? Well, it turns out that gravity is negligible because if you compare it, for example, with electromagnetic, it turns out it's about 38 orders of magnitude. Now, 38 orders of magnitude, I mean a number which has 38 zeros. I don't know how much you're familiar with scientific notation. It's a terribly big number, right? You can't imagine. On our planet, there are about 10 to 10 people, or 7 times 10 to the 9. And I guess if every one of us had as many children, 10 to the 10, there would be 10 to the 20 of us. And if each of them had 10 to the 10 children, that would be 10 to the 30 of us. Okay, still not this way. It's extremely weak. So you may ask, well, why in the world then gravity matters? I mean, why does matter gravitate, right? Why is the only force that we feel? The only force that really matters in this world, right? If you look at the planets at large distance in the sun, is gravitational force. And the answer is, I'm sure many of you know that there are many, many, many elementary particles inside a celestial object. For example, inside the sun there is an even bigger number, 10 to the 50. So you got to imagine a number with 50 zeros, right? It's a huge number. So although the force is very weak, it's a cumulative effect of many, many particles, and in the end that force matters. Okay, it's also important that we carry no charge. Planets and stars carry no charge, so the electromagnetic force is not important. But I can safely ignore it, although it's the main force in the macroscopic world, in my world of microscopic elementary particles, I can ignore it. And I can say what I said, that we have the theory, okay? Now, what is crucial in the theory that is based on symmetries, these are some complicated symmetries. I don't want to talk about them. They are called local gauge symmetries, okay? The crucial thing is that the symmetries govern and govern our understanding of these interactions. And I'll give you one example of how symmetry may be relevant for the world. And that's the first symmetry you saw, right? The first symmetry a child sees is the symmetry between left and right. We call it parity, okay? The symmetry of the images in the mirror. And if you wish, this talk is going to be a fall and rise of parity, hopeful rise. And I'm going to argue that it's actually very timely, although the ideas that I'm going to present are more than 30 years old. I want to argue that they are really timely today, and it's an exciting moment because the ideas that led to them can be tested only now, because now we have this huge Hadron Collider at CERN that has finally reached the proper energies. So if you wish, in a sense, it's a funny public talk. I should be talking maybe about the paradigm of the standard model of the established physics, of the things that you can read these days. You read a lot about that if you read the scientific journals. I don't want to do that. There are a lot of people in Ljubljana that can tell you that. Mika himself will tell you that. I mean, this is by now a textbook stuff. What I want to tell you is sort of an attempt to create a theory. I want to give you a glimpse of how this works. How you would actually try to make a theory of phenomena that have not been tested. And, you know, I've tried myself, you know, when you try to construct a theory, you hope to get into history, and most likely you end up in a dustbin of history. But I want you to see, because maybe there is some of it, the way the great physicists reason can be found here. What you do, of course, not with the same brilliance, imagination of depth. You base your work on past, you base it on data they have been accumulated, but also there is some speculation and some vision that most of the time fails. So let's see what happens. Now, elementary particles, they have properties just like us, mass. They have charge, we don't have. Then they have this funny property of spin, just like here. They keep spinning all the time. They keep spinning. It's like they have angular momentum even at rest. Okay? And it turns out that in quantum mechanics, the theory that governs the microworld, this spin has to be an integer divided by 2. And I'm sure you all know this. The first few minutes, if you don't know all of what I'm going to say, it's going to be hard to follow the rest. I want to talk about the matter, right? The things that matter to me is the world of elementary particles. You all know that matter is made out of atoms, and atoms have a nucleus in the center, and then there are little electrons, light electrons that are moving around. And you also know, I'm sure all of you, that nucleus is not elementary. That's been established a long time ago, a century ago. We know that nucleus is made out of protons and neutrons. They are almost the same particles. Proton has a charge, positive charge, neutron doesn't. Otherwise, they would be basically the same. They have basically the same mass. I call it GeV. We have funny units in particle physics. Forget what it is. The basic unit of mass for me is going to be proton mass. I'm going to measure everything in proton mass. For example, 1 gram. Again, in this world, it's extremely heavy. 1 gram is 10 to the 24. Okay, a number with 24 zeros. We are always hitting these huge numbers of proton and neutron masses. And in this world, notice electron is almost massless. That's why it can move so freely. It's 1,000 times lighter. We call these particles fermions. It's in the honor of Enrico Fermi, one of the people that played a major role in the development of what I'm going to be talking about. Their characteristic, they have a spin half. Okay, these are the guys that can be spinning either way. And there is, of course, electron, as we said. Now, in 1928, in a remarkable insight, extraordinary touch of genius, Dirac will write an equation that describes these particles when they move very fast. We care about particles when they move very fast. This is what we do in these big accelerators. Okay? And it turned out that spin emerged from his equation, which we established experimentally. Now, the forces have their messengers. In the modern picture of particle physics, we now know for sure, just as it happened here, that I have a messenger electromagnetic force. You see this yellow guy, the photon, as we call the particle that is responsible for the force between charged particles. You see what it did? It was emitted by an electron and another electron received it. And this is how somehow they hit each other, they collide with each other, they scatter, we say. Okay? So, as opposed to what Newton imagined in his time, that the forces are things that will happen instantly at a distance. We now know that there is a carrier of force. Okay? If there is a force between you and me, there is someone, there is a messenger. So you see what I showed you here, how it looked. Okay, you pick this in the following manner. Remember, there was an electron that emitted a photon, right? There was another electron to receive it, and then that's way they would interact. Okay, in a beautiful work, Richard Feynman, one of the great physicists of the last half a century, found a way of describing this, not just picturesquely. You see what I'm doing here? I have an electron which is moving, and instead of writing, showing movies, right, he has this wiggle here. It's a photon being emitted, another electron. Oops. Okay, I was going to say a very important thing is that the arrow cannot be broken. You have to follow the arrow. I'm sorry. Just notice, you see that this is wrong. Okay, this arrow should go, but there was an electron coming, receiving the photon from the first electron and then scattering. Okay. So what we do that, I mean, this is not just to show this diagram because they're interesting. We actually, we have a way of computing. We can actually calculate what is going on by using this diagram. Extremely useful. But if you don't mind, okay, in this little movie, if you got a picture of what is going on, if you can remember this for the rest of the talk, it may help you to understand some of the little few technical things I'm going to say that worry me whether you'll be able to comprehend them. So there are other forces, right? There is a gravitational force. I don't want to talk about it. It's too weak, we said. Then there is this electromagnetic force. There is a yellow photon, a messenger. There's got to be a force that keeps us together. Otherwise, there must be something that keeps this particle together in the atom. Okay? And it's got to be strong. So without much imagination, we call it strong force. It has its own messengers. A funny word. I mean, this is bad English, right? A mixture of English and Greek. Gluons, right? Because they are supposed to keep us together. Okay, whatever is the basic entity, they glue us. These little elementary particles so that they can exist. Okay, I don't want to talk about them, although they are probably the most important. It turns out that the protagonist tonight will be actually the weakest of the forces, which has interesting messengers. It took a long time to be discovered, because notice that they're very heavy. This unit, funny unit, was a proton mass, 80 times heavier than the proton mass. You had to wait for a long time, you would see, till the 80s. Okay, they were measured 50 years before that. You had to wait for 50 years. One of the main messages of the way the field evolves of particle, elementary particle, is the time. Unlike normal fields of physics, when you maybe need some months or a few years to check your results, you have to wait for decades. So it becomes very exciting to us. Okay, later, of course, it's so important that it's not clear. So these guys carry charge, and they will be the central to our story. Now, this you don't know. You know everything, but you don't know that protons and neutrons are made out of aces. And you read out of scientific literature. By the way, if you have some objection or some question, please stop me and ask me. So they're made of aces suggested by Zweig in 1964. I see nobody commenting. Well, the aces come in colors, 3 different colors. They are funny particles. For example, proton will be made out of 2 up. This is without much imagination. We call them up and down. 2 up and 1 down. And neutron will be made out of 2 down and 1 up. For all practical purposes, I don't even have to talk about these funny aces. But I will. Just you will see at the end, I will need them. They also have spin half. So they go through this sort of nicely in the story of fermions that we are going to be talking about. And then, of course, there is an electron. By the way, as we speak, you know, these are the gluons. Remember how they look? They are funny, powerful things. They are going from one of these aces to another, just to be able to glue them as we speak. Now, the world is made out of proton and neutron. This is the nucleus. And the electrons, therefore, it's made out of aces and the electron. The whole world. And yet I'll be talking mostly about the mysterious particle neutrino. It's the hero of the story. It almost doesn't matter because it doesn't interact with anybody. Okay? So maybe puzzling why it's so important. But I try to argue that that's a window to new physics, to new phenomena we are looking for. So nobody objected I call these aces. You must have read somewhere what the quarks. Now, can someone tell me what are quarks? And they're made out of quarks. This was done a little later by Gell-Mann. I don't know how in the world he managed to get all the glory. He never took them seriously. He didn't believe in them. If you read his paper, he'll tell you that he thinks they are mathematical entities, okay? Unlike him, Zweig, who was a graduate student there, so usually the great development of science have the great heroes. He's a great hero of the 60s. Gell-Mann celebrated Nobel Prize winner, but in case of quarks, it's bloody unfair, because it was actually Zweig who took them seriously. He just gave them a name, but didn't call that. Okay, Gell-Mann liked James Joyce. I love Gell-Mann's work. I never liked James Joyce, and Trieste is all about James Joyce. James Joyce spent many years writing there, and everybody in Trieste is crazy and proud about James Joyce. But you know that it's 3 quarks for Mr. Marx in Finnegan's Wake. So, hopefully you all know that, so that we can go on, okay, to the beginning of the story, which is the beginning, if you wish, of modern particle physics. It was a great bombshell when it happened that 3 years after he wrote down his equation, Dirac will finally take guts to say what his equation was predicting, okay? That if there is an electron in this world, an electron is a charged particle with whatever charge you take to be, you take it to be negative, there must be an antiparticle with exactly the same properties, same mass, everything else, same spin, but opposite charge. We call it anti-electron positron, it's a better name. Okay, it's amazing that he would take 3 years. It's not clear because as I speak, someone in my field is writing a paper and sending us to our archive. We get in the morning and we read our archive. It's been going on now for 20 years. All the papers in the world are sent to the archive. It's a beautiful democratic process that we can read the same papers here and in a small village in India. And everybody will easily suggest 2 or 3 new particles, but it seems that what you said at the time really mattered. You couldn't just speak like that. Your reputation was seriously damaged if you suggested something it was not seen. It takes 3 years to say this. Meanwhile, they have been seen actually by a number of people. A graduate student at Caltech called Chao saw it and talked to everybody that he saw this particle. They're exactly the same, except if you put them in a magnetic or electric field, they move in the opposite direction because of the opposite charge. He was seeing this, Chao. Nobody took him seriously because Dirac didn't say it yet. And as soon as Dirac said it, a colleague, he was already a professor, does the same thing and gets a Nobel Prize. This is really terrible. It's one of the badly disputed Nobel Prizes. Some years later, an antiproton will be found by Segre and Chamberlain in 1955. And then eventually there will be one after another all these antiparticles found. The point is that somehow a dogma will emerge, a beautiful dogma, if you wish. There will be a beautiful picture that for really every particle we have this antiparticle. It came out of nowhere. It was not seen, it was not imagined, okay, when originally Dirac wrote his equation, okay. And it's probably considered one of the most beautiful things in our field. Except that may not be true, says the young Italian genius Ettore Majorana, who will write this paper, one of the very few papers they have written. His last paper before he would tragically disappear. He was only 32 years old. I don't know if you know the story, some of you may have heard of him. He was taking a boat from Sicily, he was originally from Sicily, to Napoli where he worked. He needed a job in Napoli, that's why he wrote this paper. I mean, we are really, really lucky that he did because our field is based on his work. He wouldn't publish anything else almost. His body was never found. So the mystique of Majorana grew for decades. This is the search for Majorana going on. Who saw him in Italian, describing here, behind and so on. And as I said, since the body was never found, you could of course build a myth, a legend. He lived apparently for many years in Caracas. There were recently articles that he was seen in a monastery in Tuscany. Every now and then people would see him everywhere. Well, he left us a great legacy, I said, by sheer luck that he needed this paper. Now this is what Fermi, who was one of the greatest scientists of his era, says of Majorana. He says there are various types of physicists. You have second, third rank. They do their best, but do not go very far. Now, this is very sad because he thinks everybody, even the best among us. Because then he says there are first rank. They make great discoveries, fundamental for the development of science. And he mentions there Heisenberg, the father of quantum mechanics, and Einstein himself. Now, this is, I think, something personal, because clearly Einstein should have been here, probably. And then he says there are geniuses like Galileo and Newton. Ettore Majorana was one of them. Unfortunately, he lacked common sense. He wouldn't publish. Now, the way we publish today, sometimes I wish that maybe was like some common sense, okay? Now, the story, it's really a remarkable story, because not only that he will come with great ideas at the rate of once a month, he would see a neutron before it was discovered. They were Nobel Prize works, and they wouldn't be able to force him to publish, ever. He was also an extraordinary calculator, which is not usually something that goes together. Like they would have, you know, Fermi was a great competitor. He needed to beat you in everything, from ping pong to calculating complicated integrals. So he would be on the blackboard and Majorana blindfold, and Majorana would beat him. It seems very often. Even the story how they met him, Majorana was an undergraduate student, and some of the brilliant graduate PhD students of Fermi found his genius, take him to Fermi. Fermi was finishing a great work, a Thomas Fermi theory, worked for 6 months. But Majorana wants to know what he's doing, and of course you don't want to tell a student what you're doing. How can a student understand? But this guy understands. Ask a question after another, and Fermi keeps responding. Next morning comes Majorana with one sheet of paper. Wants to check the results of Fermi. Fermi is a little unhappy that his kid wants to check his results. So he said, did you get this? Oh yes, says Fermi. Did you get this? Yes, I did. Now he can't believe he worked for 6 months. This guy did it overnight. And then Majorana says, who was pathologically shy otherwise, he says, oh, then I think you're right. I'm right, then you are right. And what he did, what's going to be a theme of the talk, is something that I could call maybe exaggerated, but almost through the creation of electrons out of nothing, in 2 types of processes. Immediately after Majorana, this will be spelled more clearly by a young Italian, also Racca. It's called Neutrinos double beta decay. This complicated name I'll explain as I go along. And then some 50 years later, a little less, this is maybe the thing that I care most about, what I've done with my friend Jung when we worked at Brookhaven. And we would suggest that the same process can be seen in collider, but it's much more clear in machines like LHC that you could create electrons. Although the machine contains only protons, it has nothing to do with electrons, okay? So you wouldn't expect that this machine would give you electrons. So why would neutrinos be so special? They are most aloof of all the particles. They simply don't want to interact with anybody. And that's strange that you want to study them. Well, we do these strange things. We want to study them precisely because they don't want to interact with anybody. Therefore, it means they can give you a process where there was nothing before. And that's a window to the physics. You try to see where before the theories didn't predict anything. Now, how it was discovered, it's also interesting. Neutrino was suggested by not being seen. That time, a beta decay, a nucleus decaying into another nucleus would be neutron in a modern leg is decaying into a proton. And the electron, what was not going okay was that the energy didn't seem to be conserved. And we somehow believe in conservation of energy. It's one of the things that works beautifully in any branch of science, so we take it for granted. We try to push it as much as we can. It didn't work, and there was a lot of debate whether or not should be given up. And then Pauli suggests that the best way out is that there is a new neutral particle. Neutron, remember, carry charge. Carry 0 charge. Proton has opposite charge from electron. I forgot to say that. That, of course, the electron goes around the proton, so together they are neutral. Atom is neutral. And he actually called it neutron. Fermi later, well, apparently not even Fermi, a student of his said, well, neutron was to be found soon. He said, let's call it neutrino, a little neutron. Italian way of saying. It's like a Bradov electron. You will see it's supposed to appear always together electron. You should never be able to produce an electron without neutrino. Okay? Just the way it happens here. Okay? We call them leptons together from Greek. letter, which is light. Now this is a letter. It's an interesting letter that Pauli doesn't write a paper. Okay, well, he was so famous he didn't have to write a paper. They had a congress. They were all the leading people in the field meeting together on the issue of these radioactive decays. And he says here, it's kind of nice how he's asking, apologizing. He says, I found a desperate remedy. He says, again, notice this here, what you said better, okay? He's apologizing for suggesting a new particle here that he calls neutron, which has spin half. Remember, it's a spin half particle, okay? Even he mentions that they have a mass. This is interesting, that intuition of a great physicist. Later on, most people will claim that neutron has a zero mass. That is to say, neutrino. Okay? It's also nice to read here. His famous teacher at the bar was telling him, don't look at this, you know, it's like new taxes, you know, you drive you crazy. It seems that people worry about taxes ever since. Okay, he can't go to this meeting because he has to be present in important dance. I like that. To come to CERN. So how are we going to see this particle, okay? Well, if it's decaying like this, neutron giving a proton plus electron antineutrino, so this is not very smart. You say, let me try to do the opposite. Let me then hit the, let me hit the proton with a neutrino. I should get then, previously I had a neutron giving me this, so now I should produce an antiparticle. Notice conservation of charge. This is positive charge, so this should be positive, false positive. Okay, the trouble is that this is called mean-free path. It's a distance that the particle likes to travel before interacting with anybody else. In the case of neutrino, this is what I meant lead to interacting. It's 10 to the 20 centimeters. Now 10 to the 20 centimeters, this time I can tell you what it is. It's 70 million times the distance between Earth and Sun. Okay? This is how long the guy was dead. So this can really help us understand John Updike. I don't know if you know John Updike, who died now some years ago, a great American writer. Perennially suggested for Nobel Prize. This is what he says in his poem in the early 60s, 1960 or 61. Well, you can read it here. It starts with this interesting statement, I'll come back to it. They do not interact at all, and that bugs him, that Earth is just a silly ball to them, and so on. You know, they go through a stallion, they salt the stallion in his stall, and so on. Finally, they enter in Nepal, and here's the lover and his girl from underneath the bed. You call it wonderful, he says, I call it crass. It's ugly done to him. Okay? This is where we differ. The poet sometimes. I love John Updike. We discovered, this was the first year when we arrived at the States in New York, and both my wife and myself discovered John Updike. We like him a lot. And the interesting thing is this. Two things, he's calling it ugly. And also this claim that they have no mass. Now this is interesting. Of course you can say, poet can say anything he or she wants, right? Because there is no referee for poet. There's an editor that's going to publish it. No, he's not going to look whether it's scientifically correct. The point is that every referee in the world would have accepted at that time. There was a deep belief that neutrinos were massless. It was a common knowledge. So you can imagine when I start to tell my wife that I'm pretty sure the neutrino has a mass. She didn't tell me then. She told me some years later. She had deep doubts. She was supportive of this crazy idea. Okay? Because you can imagine she's worried. If a poet knows that neutrinos have no mass, with all due respect to her, then one greatly wouldn't be right. So how did you see it finally, although it doesn't want to interact? Well, if you have many of them, it's a statistical thing. They don't like to interact. The more you have, the more likely that one of them will interact. Okay? So all you needed is to take a large number of neutrinos. At the time, they were finally reactors, the Savannah River reactor. So Reines will get eventual Nobel Prize. He's going to wait for many, many years. He's going to have a lot of neutrinos. Again, a large number, okay? This is 10,000 billions. This is 1,000 times bigger than the number of people on this planet, so it's a large number for every second, for every centimeter square. Not surprising that you can then finally get an effect. And you get even like 10 events per hour, which is fantastic. Today, when we get so many events per year, we are happy. And what they took, of course, you need something which has a lot of protons. Well, water is the cheapest source of protons. These were good old days. I start calling them good old days. Okay? 8 people on experiment. 2 physicists, 6 technicians. The skinniest of them, this was so small that only the skinniest could actually sit inside. Okay? So it gives you size, so a sense of the size of the experiment, of the art of that they are. And neutrinos will be discovered finally. So remember that forces have their messengers, so you can imagine why I talk W boson a messenger. People imagine it to do the job that we now know is true. I'll come back to that. Neutron decays because it emits a W boson, becomes a proton, and the W boson interacts and gives us an electron and neutrino. Okay. So these little diagrams that came back is just the movie that I showed you. So let's see the movie. For the W boson, you have a neutron, which should decay. Neutron consists of 3 quarks, color quarks, right? 2 down and 1 up, if you remember in the beginning. So if I wanted to decay, it should give me a proton. Proton has 2 up quarks, 1 down quark. Well, it emits a W. Here it's a W, this funny guy. Shiny, hairy, you see how it was addicted. And it finally decays into an electron or neutrino. Okay? So this is what the diagram stands for. Okay? This is the thing that happens there. In 1956, the discovery of neutrino is a great year in this field. That's probably the second most important moment in the history of particle physics. Okay, 2 young, we can almost say kids. Look at the way they look. T.D. Lee and C.N. Young. I think T.D. Lee was like less than 30 years old. Okay, I get to know him very well because I used to work at Brookhaven National Laboratory. He was at Columbia. I did my PhD in New York, and I'll tell you later. I would challenge what he said. He didn't like my work at the time. It was not encouraging for young men to be discouraged by great physicists. This was such a bombshell that less than a year later they had a Nobel Prize, because what they suggested is that what seemed to be sacred at the time, it was believed. You see, when something doesn't happen, we start to believe that it won't happen. So this is how, you know, dogmas get created. One of the dogmas in particle physics was that parity, the symmetry between left and right, is an absolute symmetry. It was true in every process they saw before. There were anomalies that the only way out, they suggested, would be that parity is actually violated. And that maybe only left-handed particles, only particles that have left part, let's imagine as if there is some kind of invalid picture of a particle should participate in this process. And left-right symmetry would be badly broken. And the experiment, they suggested even the experiment was performed by, it's always said Madame Wu. You have to emphasize that there was a woman. There were so few great women, so few women scientists. Okay. These are good old days. There are 5 of them on an experiment. They performed the experiment. What they find is not only the parity is broken, but the parity is maximally broken. So if I want to define parity, left-right symmetry, I have to define left. So here, I can tell you what is right if I define left, right? But I have to tell you something first. So they defined it this up direction, let's call it left. And you would expect there in this experiment, this is cobalt decaying one nucleus into another, neutron into a proton, that if there are 100 electrons coming out of here, 50 of them will go down, which will be right, and so let's call this right, 50 now will go left, and 50 will go right. What was observed is that they would want to go down and not up at all. Okay? Some kind of maximal parity value. So it was really a shock. Not only was not a good symmetry, it was a terrible symmetry. It was badly violated. I think she would have gotten a Nobel Prize, although they suggested the experiment. She wasn't sure of herself. So she asked people at Berkeley to do it. One of them was Lederman, who would later become a great experimenter. He just started out, but they repeated her experiment and agreed with that. So for us, what is important, that in this process, the messenger, the W boson, the parity relation means that only the left part of you interacts, okay? Only left-handed particles say interacts, okay? Which was confirmed when it was discovered, and it was discovered only in the 80s at CERN in so-called super proton cyclotron SPS experiment. These are now modern times. There are 137 people. It's a 7-kilometer circumference. It's still sort of finite size. You can jog around it. And people did. I remember near Chicago, there is a machine, Devatron in Fermilab, similar size. And my American friends, they always wanted to know how much they run. So we would run there. I found it very boring when we go running. It was better than running in a small circle. Anyway, so the W boson, you see, what it does, it takes a quark into a quark, right, neutron into a proton. So you can produce it if you have quarks inside your particles in the accelerator, and this was the accelerator proton hitting on an antiproton. These experiments are grandiose in some sense, and yet a little primitive, right? It's like you and I wanted to know what this is made of, so we hit it against the wall and then look at the pieces, right? That's what you do. You take very energetic particles, hit one against the other, and wait that something dramatic happens. And finally, they saw the W boson. For this, you needed a lot of energy. Once again, the unit is the proton mass. Now the energy is 200 times bigger than a proton mass. This is a huge energy. And soon, when this was found, this would be upgraded into lab experiment, large electron proton collider, large electron positron. These are modern times. Look at how many people, 1,500 people, the huge detectors, 27 kilometers circumference. You produce billion W boson, and this is why we have in high precision the standard model. When you have a billion particles, you can study them. We call them a factory of these particles, okay? At proper energies. Let's see. See, this was the first accelerator that you used to find the W boson. This is a little one that you use to inject particles that are accelerated here. You see, when you have these accelerators, it's an art of choosing the proper size. It's a very tricky thing. I don't know how they decide finally. It's a very tricky thing. Because when you accelerate them in the circle, you're losing energy. It costs you. They are being slowed down. So ideally, you would maybe do it linearly. But if you do it linearly, you cannot keep accelerating them, right? So you have to optimize between a small and a big circle, depending on the energy you want. So this is this monster. I'll show it later in the modern version. And this is now, I think, somehow you have the arms to understand what I'm going to tell you. This is what my Rana program is. So let's now try to see what, now that we know what the messenger of the force is and how you see. He says that neutrino may be equal to anti-neutrino. What it means basically, this I cannot explain here, that such a particles, he says, would have a mass. And this is a great intuition. It suggests strongly that neutrino has a mass of such a nature that it basically can disappear, if you wish, into nothing. I'll show you a movie so that give you a picture of what is going on. And this is why we can create electrons out of nothing. Okay, I'll give this technical diagram just once. Maybe I went too fast. Yes, sorry. You see, sometimes a beta decay cannot take place. Why? Because the daughter nucleus, for example, germanium cannot decay into arsenic because arsenic is heavier than germanium. You cannot decay into something that is heavier than you. It should be at least lighter than you, right? You're going to get something else. Okay? So then, what can happen that you get a double beta decay because selenium is lighter than germanium, but it has 2 protons more. So I have 2 electrons and 2 neutrinos. This is what is happening, okay? Now, however, if neutrino has a Majorana mass, I can complete this process, these guys kind of disappear, then I have a creation, what I've been calling, of electrons. I still a process in which I start purely with nuclei, and I get only electrons. And only if neutrino is massive. And this is how it looks, okay? I guess the movie should help us see what is going on. Now you have 2 neutrons, right? 2 down quarks, 1 up quark, okay? And what they do the down quarks turn into up quarks by emitting these funny guys, shiny guys, that will themselves give you 2 electrons and neutrinos, and according to my Arana picture, they can just disappear. Okay, this was a sort of bombshell when it was realized that this would take place. Suggested in 1937, still looking for. You see the time scale, our field. They're talking about 80 years. We are still, and of course now it became sacred. When you look for something for 80 years, right, it's holy grail, right or wrong. And these are modern times. Experiments are bigger. They'll say, I don't know, I keep saying, you know, good old days and modern times. You may say it's my gray beard. I can't help feeling some nostalgia for those experiments when there were 2 people who could be inside the detector. This is the size today. This is the experiment, Gerda experiment. The name is just an acronym. It's in Gran Sasso Laboratory in the Italian Apennine near Rome. They're famous mountains. They became infamous or famous. I think it was 1943 or 44. I guess you should know some history. When it was a famous Nazi commandos came to liberate Mussolini, who would be recaptured later. Actually, it's funny because now it's a great laboratory. They often have congresses there. I remember my first congress at Gran Sasso in December. It's a very strange thing. There were just us, maybe just before the tourist season, early summer. And there was a bunch of Nazis having a meeting on this particular event. It was a bit strange. They were forgiven, I guess. We hope that you know, it's gonna, as you have said, it's gonna take a few years at least to get the first data, and maybe about 5 years to get to the right numbers that we can check the work on my Rana, okay? Now what we have to say, what does the theory say? And this is a hard part. This is a standard model, okay? I don't want you to understand the standard model. I surely can't explain it to you, but what I want you to see, what is essential there. What bugged me when I started out my graduate school, somehow I said this cannot be true. This is the way they imagine. Glashow Weinberg, great American physicist, together with Salam, my first director, the guy who founded the International Center where I work. I invite, if some of you are interested to think really mind-boggling international center. This is the most international you can get. We are very proud that we have people from all parts of the world, all parts of the world. And the afternoon in our bar is full of different languages and colors. It's a beautiful place, I find. Okay, he had this vision to bring people, literally, as I said, from all over the world together, from places in which there is great science and people who are developing today. So it's playing a good role in democratic scientific process. Now, what they imagine, and he was the father of this idea, of this terrible breakdown of parity after TDL, that you see, what I want you to see here, that the left-handed, this is the electron, the left-handed electron and the left-handed neutrino, they're like buddies. This is, you know, you can say almost like twins. Well, the electron carries charge, and they live together. This is why I've written it this way, okay? It has an important physical meaning. What I want you to notice is that the right-handed electron is left alone because they said that there is no right-handed neutrino. They were very proud. It was a very predictive theory. One of the predictions was the neutrino had to be massless, so none of the things that I told you about would take place. Okay? There was a firm prediction. Okay? There was a structure of the theory. There was no left-right symmetry to start with. So if you wish, the question that maybe you want to ask, you know, the way the child asked, well, why is this symmetry, such a natural symmetry? Why would it be so badly broken? Okay? They would tell you, don't ask. Shut up. Keep calculating, because it's broken, it's maximally broken, and it's broken forever. There is nothing you can do about it. I don't know. This is how I feel. Can be. Well, you can read it. God may be left-handed, but she cannot be an inward. I can't believe that. Well, it wasn't just me. There were a few of us. No, how would you make the world left-right symmetric? Well, as Nike tells you, just do it. And this is what, actually, the seed ideas came from Salam himself. This is interesting. He would kind of regret what he was saying before. And I was just starting my graduate school when I ran into this paper and I did my work, and this would make me believe the neutrino has a mass and worry my wife and other things, okay, that I will be doing, strange things. Well, what they said, what if the world was actually left-right symmetric, okay? Then they said it cannot be done. It was very strange. It was one of the things I would like to mention, the way the science develops. It's great. Even great physicists sometimes don't do obvious, so there is room for everybody. They suggest and fail. But the idea would be to have the world symmetric, and of course that means if there is left, there is right. So if there is left neutrino, there is right neutrino. You cannot say that it's not there. It must be completely symmetric. So if there is a W that interacts with these guys, remember the W interacted only with left guys, there must be another W, and that W is going to be heavier, of course, much heavier, because then you need more energy to see it, and we didn't have enough energy. That's easy to say. And when you reach those energy, parity would be restored. The trouble is they said that it cannot be done, and this was shown later by Patra and myself. And how would it work? Now imagine, this is sort of, and it's so easy that it's surprising that they would make this statement. Imagine imagine this could be a little mountain, right, with two valleys. And imagine there is a big object here. This manifestly breaks symmetry between left and right, right? If you come here in the morning and see this, you're going to say, well, there is no left-right symmetry, right? Here, there is nothing here. There is. Well, except that if you had a giant, if you had someone strong enough and big enough to put a ball back there, this now is left-right symmetric, you agree? Completely. Except that it doesn't seem to be stable, right? If there is little place and there is no friction, this ball is going to fall down. And it can fall down left, it can fall down right. But it will fall down. And it decides. We call this spontaneous symmetry breaking, okay? This is what I've shown would happen very easily in this kind of theory. And actually the example that Salam later gives, it's very nice. He says, suppose you go for a round table dinner. Imagine some important people. Now what happens? You have glasses both on the left and on the right. You don't know which glass to take. Let's say there is really an important person. At ICTP, at my institute used to be him. And he would take people for dinner. Everybody waited. Salam takes the glass. So he would decide whether it's left or right. Once someone takes it on the left, everybody else is going to follow. So the symmetry will be broken, although originally there was a theory. There was a symmetry. Now, what happened in the theory neutrino was predicted to have a mass? You see, when I said that there is a right-handed neutrino, now neutrino electrons are completely the same. There is no difference, and therefore we predicted neutrino to have a mass, and we couldn't explain to people why this mass was not seen. Why was it so small? So there was a curse, and we were worried for quite a while. We worked for some time. The solution would emerge, and what happens is that it's called the seesaw mechanism. In the process of that symmetry breaking that I discovered, the right-handed neutrino gets a large mass. And through that, this is a cartoon of what is going on. Okay? That's why the name seesaw. The name, one of the people that would do this in parallel in the different contexts was Gelman himself, the father of quarks, or one of the fathers, let's say. He was good with names. He called it seesaw. So what was a curse became a blessing. We predicted neutrino mass, as I'm showing here. And the question, of course, was the scale. At which energies you're going to find this new gauge boson, okay? This can be studied over the years. And what is emerging recently is that the scale is very large, but not terribly large. You will see, it's not science fiction anymore as it was 20 years ago. Okay? One of the reasons that I'm very excited about this, I find myself working maybe more than when I was in graduate school. Well, I have great collaborators. I'm having a lot of fun with my younger collaborators. One of them is Ika here. We have looked into this carefully. It's now a year or two that we are studying this a lot. And so, okay, if you wish, this is the new WR. It's a big dog. You know, in English, big dog. Big dog is a macho. It's a dominant. Okay, you have to find this guy. Okay, this is a big dog in this game. Meanwhile, what I have to tell you, and this will be a beautiful public lecture in itself, how we learn the neutrinos are massive. And it's a serious public lecture, it will take time. I just ask you to believe, to accept it, that in a Kamioka mine in Japan, very deep down, 1,500 meters, look at the modern times. Look at the size. This is a boat going around to check their photo tube. Okay, it started with a little detector. It's only the skinniest guy to be in. Okay? And that's why we need huge detectors today. This is why we need, no, sorry, not that's why we need, because now this, actually they look at neutrinos, they come from the atmosphere. There are lots of neutrinos. These neutrinos, once they are produced, and they are produced in the sun, say, they are produced everywhere, in the stars, whatever, they just keep traveling. So then they come from the atmosphere, and unfortunately it's not a reactor, you can't control the number, right? The reactor had 10 to the 13 was the number, was 13 zero, it's small, and that's why I need it. Detector, what we learned is neutrino mass is non-zero. It's very small. To give you an idea, it's 1 billion times smaller. It's around this number, 1 billion times smaller than the proton mass. Okay, this is why probably the dogma of neutrino being massless true. This is why Updike knew. It was hard to see. So here is one technical thing you will forgive me. If there is this process that I call production of electrons. Remember we saw it, if neutrino has a mass, through this diagram we would produce it. Well, the U theory says if there is left, there is right. So it's not surprising that Mohapatra and I would suggest that there is also this diagram. It's kind of trivial, right? Now there is WR, where there was WL, and there is a right-handed neutrino where there was left-handed. Okay? This is not being smart. Now what we did recently, what I want to tell you, and again, it's Miha and my student Elo and Nestor Misani, who is a Grasasso. We took seriously this scale. You see, this is the scale of 1,000 proton masses. It's a huge scale. We took it seriously and decided to look into this kind of processes to see what is the connection with the colliders. Now, you may tell me what in the world is going to connect this process in which 2 nuclei give me 2 other nuclei and electrons with a collider. A prepared experiment, right? It looks crazy, okay? But it's rotation in the plane. Just rotate this diagram. You see why they are so useful, these diagrams. I know they may be hard for you to understand it. But if you do rotate it with me, you get the process now like this. All of a sudden now, we have quarks here coming in. I've just oriented them differently, okay? When you realize this little thing, you realize there can be new physics. And that you could produce this new W boson that would then complete this picture. See, there will be 2 electrons. This is because the original diagram was the diagram with 2 electrons. These were 2 nuclei here. I just depicted them as quarks. And therefore, I would have here quarks coming out, okay, and WR again. And this is now what collider physics means. So what is this? Why are we so excited that this may be a situation of today? I should wrap it up. This is Large Hadron Collider, LHC, that the whole world keeps talking about. These are really modern times. Look at this monster. Well, it was built before. Okay, it goes under the little town. This is Swiss-French border. And it goes under little towns, okay? There were debates before where people were not so happy, but eventually they accepted that it's not dangerous. But you hear the stories about black holes being produced and it's following us all, okay? Don't worry. As I said, it's 27 kilometers. It's very deep. It goes up to 175 meters at its deepest point. Okay? And this is how it looks. You have protons accelerated on protons. They keep doing that. Notice that there is a very strong group here in Ljubljana. There are 2 big detectors. One is called Atlas, and Ljubljana people are working in Atlas. And there is, I don't know why it came out that Zagreb is so little. They didn't like it when I gave a lecture recently in Zagreb. I'm sorry. At least Ljubljana is big, right? I was born in Belgrade. I'm actually an old family from Split. It's accidentally. So, and the energy is enormous. You see, this is why this huge number of thousands are now reality. Okay? 7,000 GeV, 7,000 proton masses. It was great 20 years ago when we had 200. Okay? So this is an extraordinary achievement in technology, and some of the people from Joseph Stefan who come to talk to you about this. It's working to an incredible degree. It's working much better than we thought. It's producing more events than we should. Okay, this is sort of unbelievable. Normally you fail, right? You promise more. Okay, these guys are about a factor of 5 better than what was expected. Okay, they just shut down for a while. These two, the other experiments going on. They're going to double the energy in 2014. So it's going to be really a monster. And this is more than times. It's impressive, but I feel nostalgia for that good thing. There are 3,600 people on one of these detectors. This is CMS, compact muon solenoid. There were. Look at this. Well, what it's doing was this diagram that I showed you. I'll show it once again. You forgive me if you didn't catch it, but if you did, maybe you would appreciate the point, why we find it so exciting, okay? It's catching up. This is becoming, you know, mostly when you hear about LHC, it's supposed to find a magical particle that I didn't want to talk about here. It's called the Higgs particle. It can be a lecture in itself. It's supposed to discover things like supersymmetry, those of you that read things, extra dimensions, they say, and so on. This is catching up. We've been watching out carefully in the last year or so. I've been trying to make this propaganda for some time, but I see a huge difference, and I think Micha would agree, the last year, especially in the last half a year. I gave a lecture at CERN. It was nice to see in the summer that they were actually full, the auditorium, that this is taken more seriously. Because I want to argue that, forget these exotic things that I'm telling you that may be exciting. What we can see is sort of the cornerstone of its old static, which was the symmetry between left and right. If I produce this guy, you see, I would see this world will become left-right symmetric because there will be exactly the guy like the W boson, okay, only heavier. I would see two things. I would see the production of electrons, and this would be a violation of electron number, search for 8 decades. Well, in the first process that Majorana and other people envision, it's a nuclei giving you 2 electrons. You can never know who is responsible for this. But here, what we do in these experiments, they actually measure the energies of these guys. The quarks here become very, very energetic, become crazy. We call them jets. They look like jets, you know, when they're very fast, full of smoke. You can identify them, you can measure their velocity, their energies. Therefore, these people at LHC, and I mentioned they're both studying them seriously, can actually reproduce the properties of these particles. So what we said, you see, in 1983, I can't wait. It's becoming reality. It took us 30 years. And both CMS and Atlas have dedicated groups that are searching. And this I said already. Stay tuned. Data coming well. What I wanted to tell you tonight is that this Large Hadron Collider can hopefully probe the origin of neutrino mass that we wanted to know now for years and years, and can resolve this, I find, even to me personally more important, the mystery of the symmetry that's been interesting us for now 50 years or so. Thank you.
Kakšno vprašanje? No, dajte no, kdo te prvi. No, kar prosim.
Oh yes, I should have mentioned that. I'm glad. I'm glad you did.
Measured the speed of neutrinos.
Right. They send. Well, it's sort of this experiment is interesting for a number of reasons. One, they send neutrinos from CERN, And look at them at Gran Sasso. Sort of nice. You see, this is what these crazy guys do. They travel through us, okay? So you can send them 780 kilometers away from the place you're waiting for them. They're famous for a number of reasons which I find a little funny. The first funny reason is that the Secretary of Science of Italy, situation in Italy is troublesome in the times of Berlusconi. People don't believe me because they tell me we also have troubles. We also have dumb people. You may talk to Slovenian, to Croatian, to English, okay? But normally your Secretary of Science doesn't say the following. She congratulates the great Italian team for a great achievement of finding this miraculous new violation now of a sacred law. These neutrinos are supposed to move faster than the speed of light. So you can forget the theory of relativity of Einstein. And she congratulates this great team for having done this through a tunnel from CERN to Gran Sasso. No, I think if you spend a little time, we were discussing actually, I remember on the same evenings, trying to remember which are the biggest tunnels in the world. And what would you guess? Someone would tell me the number, what would you guess? Well, it's going to be some. Used to be Mont Blanc in the past, now it must be like 50, 60 kilometers, I'm not sure. I think there is something in Japan, there is La Manche, right? So I think she imagined maybe there was a little tunnel, a little neutrinos. So anyway, so this is funny. The funny thing is that the world took this seriously. When people ask me what to think about it, I say that I laugh, but then who loves last, loves best. So I just, since everybody asked about this, I want you to leave this room, not just with this message, but at least to remember that I stuck my neck out. That I'm saying, if they ask you what did Goran say when he was there, I'm saying there is a mistake. Neutrinos, my beloved neutrinos, are just as normal particles as electrons, I assure you, and protons and quarks. Therefore, they are not superluminous. Actually, what you can do, there's a nice paper today on Archive saying that there will be very serious possible statistical error. There was a seminar, but we were away. Both Micha and I were in the States recently on a conference which this was discussed. Well, I have one of my colleagues in Trieste, my only colleague in my group is Alexei Smirnov, which is a celebrated authority on neutrino tomology. He said that these people, that one of the representatives couldn't answer very well the synchronization of clocks. You know, they use the satellites and whatnot. It's not clear whether they do such a good job. But today we've seen a paper that says that there may be a serious statistical error. There is also a nice paper by Gleshow, one of the fathers, remember, of the standard model, who wrote a paper with Cohen recently saying, if this were true, you would have seen in the experiments like superconductivity a much bigger effect. So I'm sure. I'm sticking my neck out, and I want you to remember these experiments has a serious error. And it doesn't mean that they are bad experimentalists. What I think is bad that they made a press conference. I decided to doubt them because if you're serious, you wouldn't do a press conference before you send the paper out and let your peers judge it. I find it bad taste. Okay? To excite the world before you test it. But I just want to tell you that some 20 years ago, give me a second, there was a similar dramatic thing in Seattle. A group of brilliant experimentalists were finding a new force which would show that the Newton-Einstein law of gravitation was wrong. According to Newton and Einstein, the force between you and me of gravity is inversely proportional to the distance, turns out squared. They were finding deviations. And they were so good, this is beautiful, that they took into account the following fact. In Seattle, it rains a lot. My daughter was studying there. She was complaining about rain all the time. It's beautiful green, but it rains all the time. So there's a little hill near the physics department. And it rains a lot. They took into account the change of gravitational force due to the rain when it falls down on the hill, becomes heavier. What they didn't take into account is that Westinghouse, they're using apparatus from Westinghouse, used bad conversion of inches to centimeters. And it was written to 4 decimal places, 2.5432, so you don't doubt it. I think that NASA had a similar problem, right? There was, so I'm suspecting there's some little treasure. Well, I don't know.
The superconductivity experiment was measuring the neutrinos from the sun. And they move
a different energy, right?
Yeah,
but
also they are not perpendicular to the force of gravity.
You could still argue that. I agree with you. You could still argue. You could maybe wiggle your way out.
I personally imagine that neutrinos take shortcut because we have a space-time curvature in four dimensions, and neutrinos somehow make shortcut.
Well,
is that possible?
I don't know.
That would also mean that
I don't know.
why they don't interact. So
We often discuss that. Well, I maybe tend to be a little conservative. You know, there is always the thing that you work with your younger collaborators, friends, postdocs, and people who should be making their career. It's a good time to write paper on this because you can get a large number of citations there. Every day there are like 10 papers on archive discussing this. And one of my friends, we were in New York at that time, right? Was actually working on some similar ideas. I think what happens is I myself cannot get excited about something which is not seriously tested. I can't. Either if you tell me that you had a theory that predicted it before, this is then beautiful, okay? But hooking up complicated explanations to explain untested facts, so I can't get excited, but it's possible. It's possible also that there are some kind of effects in nerves, very strange thing. Our friend Wally, a famous physicist, wrote a paper saying there could be maybe some new gravitation-like force which is sourced by Earth itself. Okay? It gets very hodgepodge. The simple theories that we have would suggest that this is wrong. So I'm... They showed this, right?
So
it's right. Well, look, this is an emotional feeling. If you make a press conference before your paper is tested, you're not as serious as you should be. Therefore, it's more likely that you made a mistake. You may be brilliant. By the way, one of the people on this experiment is the son of Rubia. Rubia discovered W boson. There was his photo on he's a celebrated annual Nobel Prize winner. Well, he was infamous before discovering W boson. There were a number of anomalies he would discover. He would make press conferences. These days, you don't have to be so worried, it seems, as in the days of Dirac and Pauli. You can say things.
Še kakšno vprašanje? No, če ga ni, bi jaz še enkrat prosil za en lep aplavz. Spati treba, mimo grede, ko se boste dobro naspali, gledajte se naslednji teden, v četrtek vidite na naslednje predavanje, ki boste producirali pa predavanje do 6 metrov. In sicer, če vas zanima, kaj se zgodi, ko krompirja, vidite, da boste takrat zvedeli. Malo virusi, ki pa krompirju, pa kaj taka. Potem bo en teden malo oddiha, da se boste lahko oddihali. Za tem tednom pa pridejo mesec 4 tedni vsak četrtek predavanje. O toksikologiji, o alžni biomasi, o kolesterolu, sva še o netopidih, da boste lažje pričakali dolgo leto. Uživajte, pa se ljubimo. Ko boste šli ven, boste videli, da se lahko prijavite na novice.